Hello dear students, in continuation with our discussion of previous session, in this session we will try to understand the various aspects of that binding energy property of the nucleus. So in our previous session we had a discussion on the liquid drop model of a nucleus and how this model has been used to calculate the binding energy of the nucleus, which is one of the important property of the nucleus. Then one of the scientists named as Weizsäcker has developed the formula which is called as the semi-empirical mass formula, and this formula is used to calculate the binding energy. So in this session we will have a discussion on the liquid drop model of a nucleus in brief, because we have already discussed in our previous session, and after that we mainly focus on the discussion of this semi-empirical mass formula. So this liquid drop model of the nucleus considers the nucleus as the spherically shaped liquid. So by considering that nucleus as the spherically shaped liquid drop, then the nuclear properties such as the binding energy can be described in terms of different terms, that is volume energy term, surface energy term, Coulomb energy, asymmetry energy and pairing energy term. So all these terms are involved in that semi-empirical mass formula, which is used to calculate the binding energy. So the basic assumption of this liquid drop model is the nucleus is the spherically shaped liquid drop. Then in this liquid drop model, or using this liquid drop model, one can easily calculate the binding energy. So what is binding energy means? Amount of energy required to separate the nucleons from the nucleus. Means initially we have certain nucleus, and to that nucleus we are supplying certain amount of energy. So after supplying that energy from that nucleus, the protons and neutrons will get separated. So that amount of energy required to separate Z protons and N neutrons from the nucleus is called as the binding energy. So that is amount of energy required to separate protons and neutrons from the nucleus is known as binding energy. So by considering that liquid drop model, one can develop or one can construct the semi-empirical formula. So why it is called as semi-empirical formula means it involves partial theoretical predictions and partial experimental data. Then the mass of the nucleus, mass of the any nucleus is given by this formula, that is Mn is equal to Zmp plus A minus Z into Mn minus B of A comma Z divided by C square. So the LHS is mass of the nucleus Mn. The first term of RHS is Z into Mp, means Z is the atomic number, that is number of protons multiplied by mass of one proton, plus A minus Z gives the number of neutrons into mass of one neutron minus binding energy. So if we know the binding energy, we can calculate the mass of the nucleus. If we know the mass of the nucleus, then we can calculate the binding energy by rearranging the two terms, that is mass of the nucleus can bring into this right hand side, and this binding energy can take it into that left hand side. So by rearranging those terms, we can calculate the binding energy. So in the previous session we had discussion up to this formula, that is binding energy. So this binding energy means one of the other quantity using this binding energy is defined as the average binding energy or the binding energy per nucleon. So in order to plot that binding energy curve, one can require that average binding energy or the binding energy per nucleon, that is binding energy divided by mass number is the average binding energy, and in that binding energy curve this average binding energy is maximum for iron 56, whereas it gradually decreases for larger mass number nuclei, that is for more massive nuclei. So after this, the main important concept of today's session is this semi-empirical mass formula, which was developed by the scientist Weizsäcker. That's why it is called as Weizsäcker semi-empirical mass formula. So according to this formula, the binding energy consists of 5 different terms. So what are those different terms? So the binding energy term or equation according to this semi-empirical mass formula is binding energy is equal to EV minus ES minus EC minus EA plus or minus EP. So it has 5 different terms. So what are those 5 different terms? The first term EV represents the volume energy term. The second term ES represents the surface energy term. The third term EC represents the Coulomb energy term. The fourth term EA represents the asymmetry energy term, and the last term EP represents the pairing energy term. So according to Weizsäcker, the semi-empirical mass formula which is used to calculate the binding energy term has 5 different terms: volume energy, surface energy, Coulomb energy, asymmetry energy, and pairing energy term. So we will discuss one by one. The first term is volume energy. So according to liquid drop model, the nucleus is spherically shaped nucleus, means the shape is spherical, which is analogous to the shape of the liquid drop. Then if there are a number of nucleons, that is number of protons plus neutrons, then means a number of nucleons present inside that spherical shaped nuclei, then the total volume of that nucleus is directly proportional to the mass number, that is total number of the nucleons present in that volume. So each nucleon has a binding energy which binds it to the nucleus. Therefore, we get a term proportional to the volume, that is proportional to A, means the volume of the nucleus is directly proportional to its mass number. Therefore, the first term, volume energy term, EV is equal to, or EV is proportional to A. So in order to remove that proportionality sign, a constant has been introduced here, that is AV. So AV is nothing but volume energy constant. So volume energy term is AV into A. So this is the first term. So how this term comes means the volume of the nucleus is directly proportional to its mass number, which is equal to number of protons plus number of neutrons. So the first term, volume energy term, is equal to AV into A. Then the second term, surface energy term. So if we consider the nucleons, that may be proton or neutron well inside the nucleus, so that nucleon is surrounded by more number of nucleons than the nucleon which is at the surface. Therefore, the nucleons at the surface of the liquid drop or of the nucleus only interact with other nucleons inside the nucleus. So in comparison with the nucleon which is well inside the nucleus is surrounded by more number of nucleons, then the nucleon which is at the surface of the nucleus is surrounded by less number of nucleons. So because of this reason, there is a decrement in binding energy, or these nucleons which are at the surface interact with other nucleons which are inside the nucleus. Therefore, their binding energy is reduced. Their binding energy means the nucleons which are at the surface experiences lesser binding energy, means they are having a smaller binding energy than the nucleons which are well inside the nucleus. Therefore their binding energy is reduced. This leads to the reduction of the binding energy. So because of this less binding energy of the nucleons which are at the surface, the total binding energy is reduced. So how to calculate this total binding energy? So the basic assumption of this liquid drop model is the shape of the nucleus is spherical. So the surface area of the sphere is 4 pi r square. So that is the formula for surface area of the sphere. Then we all know that the radius of the nucleus is given by r is equal to some constant into a raised to 1 by 3. So radius is proportional to a raised to 1 by 3. So in the case of sphere, the radius is 4 pi r square. 4 pi is the constant. So r square means here nuclear radius is proportional to a raised to 1 by 3. Therefore r square means a raised to 1 by 3 raised to square. So this becomes a raised to 2 by 3. Therefore the reduction of the total binding energy to the surface is proportional to the surface area of the liquid drop, which is proportional to a raised to 2 by 3. So how this a raised to 2 by 3 term comes means, so the surface area is 4 pi r square and the nuclear radius is r is proportional to a raised to 1 by 3. So because of the r square, this a raised to 1 by 3 square means it becomes a raised to 2 by 3. So as this surface energy results in reduction of total binding energy, so this term comes with negative sign, that is minus of as into a raised to 2 by 3. Again this as is the constant which is introduced in order to remove that proportionality sign. So this is known as surface energy term. So the surface energy term is minus as into a raised to 2 by 3. So this is the second term, that is surface energy term. The third one is Coulomb energy. So we all know that the nucleons, even though there are only positively charged particles and neutral particles, a strong nuclear force is responsible to hold those nucleons within that nucleus. So because of that reason, the binding energy is mainly due to the strong nuclear force. Even though there is a binding energy because of this strong nuclear force, there will be reduction of some amount of binding energy, which is mainly due to the Coulomb repulsion between the protons, because the protons are positively charged particles, as the like charges always repels each other. So because of that reason there will be a reduction in binding energy because of that Coulomb repulsion between the protons. So this Coulomb repulsion term is the Coulomb repulsive force is responsible for this Coulomb energy. So this Coulomb energy term is proportional to the square of the nuclear charge Z, and in accordance with Coulomb's law, it is inversely proportional to the nuclear radius. So R is proportional to a raised to 1 by 3. Therefore the Coulomb term is proportional to 1 divided by a raised to 1 by 3. So it is directly proportional to the square of the nuclear charge, inversely proportional to the nuclear radius. So as this Coulomb energy term also reduces the total binding energy, so because of that there is a negative sign. So minus AC into Z square divided by a raised to 1 by 3. So here AC is the Coulomb energy term. This is the third term. Then the fourth one is asymmetry energy term. If we consider any nuclei having equal number of protons and equal number of neutrons. For example, if we consider oxygen 16, it is having 8 protons and 8 neutrons. So for such nuclei, this asymmetry energy term is 0. So this asymmetry energy term arises only because of excess number of protons or neutrons. In most of the nuclei, that is heavy nuclei, there will be excess of neutrons. So this asymmetry energy is mainly due to excess number of neutrons. So the fractional volume of the nucleus in which excess neutrons are present will be proportional to the term n minus z divided by a. So it is proportional to n minus z square divided by a, and it is due to the change in number of protons and neutrons or the excess of neutrons. So this asymmetry energy term is mainly because of excess of neutrons, and this excess of neutrons is given by the term n minus z whole square divided by a. So as this excess number of neutrons also results in reduction of total binding energy, so it comes with the negative sign. So minus of a into a, that is asymmetry energy term, a into n minus z whole square divided by a. So this n minus z can be written as a minus 2z, because n is nothing but a minus z. So a minus z means it becomes a minus 2z. So we can write this asymmetry energy term as minus of a into n minus z square divided by a, or minus a into a minus 2z square divided by a. Both are same, because n minus z is equal to a minus 2z. So this asymmetry energy term also reduces the total binding energy. Therefore, this term also comes with the negative sign. So this is the fourth term. Then the last term is the pairing energy term. So this pairing energy term arises because of the pairing of the nucleons. Experimentally, it is found that two protons and two neutrons bind more strongly than one proton and one neutron. So experimentally, scientists have found that the two protons and two neutrons bind more strongly than the single proton and the single neutron. So in order to account for this experimental observation, there is a fifth term, that is pairing energy term. So this pairing energy term is having three different forms, means the nuclei can be classified into three different types based on the number of protons and number of neutrons. Means if the number of protons and number of neutrons is even number, then such nuclei are called as even nuclei. Means both proton as well as neutron number are even. Then if they are odd numbers, then such nuclei are called as odd nuclei. Means proton as well as neutron number is odd. Then one is even and another one is odd. Such nuclei can be classified into even odd or odd even nuclei. So based on this, for even nuclei, means proton and neutron number is even, this pairing energy term having positive form. If the nuclei is odd, then it is negative, and in the remaining two cases, that is odd even and even odd, it is 0. So that's why this is having term plus or minus AP divided by a raised to minus 3 by 4. So AP is the pairing energy term. So plus means when it is even nuclei, minus means when it is odd nuclei, and it is 0 in the remaining two cases. So this is the pairing energy term. So together all these 5 terms constitutes that semi-empirical mass formula which is used to calculate the binding energy. So therefore the formula for total binding energy becomes binding energy is equal to AV into A, that is volume energy, minus AS into A raised to 2 by 3 surface energy, minus AC into Z square divided by A raised to 1 by 3 that is Coulomb energy minus AA into A minus 2Z square divided by A, that is asymmetry energy, plus or minus AP divided by A raised to minus 3 by 4 is the pairing energy term. Then the constants of these 5 terms have been estimated as the volume energy constant AB is equal to 15.5 MeV, surface energy constant AS is equal to 17.23 MeV, AC Coulomb energy constant is equal to 0.69 MeV, asymmetry energy term AA is the 23.285 MeV, and the pairing energy constant AP is equal to 12 MeV. So by substituting all these constants and the mass number and the atomic number, one can easily calculate the binding energy. So this is the semi-empirical mass formula which is used to calculate the accurate values of the binding energy. Then if we plot the average binding energy, that is binding energy divided by mass number against the number of nucleons or the mass number, and this plot is known as binding energy curve. As we discussed earlier, this average binding energy is maximum for iron 56 and it starts to decrease gradually as the mass number increases. So for iron 56 it is maximum, and as the mass number increases it starts to decrease. So this is about the semi-empirical mass formula, which is one of the important concept which is used to calculate this binding energy. So the summary of today's session is: what is liquid drop model, what is binding energy, and how this binding energy has been calculated using this semi-empirical mass formula, which was developed by the scientist Weizsäcker, which has 5 different terms: volume energy, surface energy, Coulomb energy, asymmetry energy, and pairing energy. So in the next session we will have the discussion on how this liquid drop model explains the nuclear fission, that is splitting of heavy nuclei into two lighter nuclei. So how to explain or how to understand that nuclear fission with the help of this liquid drop model, and one more nuclear model, that is shell model. So we will have discussion on these two concepts in the next class. Thank you.